dimensionally consistent. Should be dimensionally what? Consistent. So that one we have already finished that, but today we want us to see how do we derive equations using dimension. Okay? Sorry, I was still checking someone. Okay, we said we want to use it on how to deriving equation. Every time we are supposed to start it, but this one needs a lot of time. But I believe you are a good student. We are going to move through it very fast, and then we'll see how fast we can move in that. Stephen has gone away. I don't know what is the problem. Is this network? So we are saying that the method of dimension analysis, is used to obtain an equation which is relating to the relevant variables. So which means here we shall look at variables. We shall look at variables. And those variables I'm talking about I'm meaning quantities. Those physical quantities that we have looked at them. But should be derived quantities. They should be derived quantities. Then these derived quantities, we shall relate them with the fundamental quantities that we have already seen, with the fundamental quantities. So to help us understand this concept also better, we need also to remind ourselves of proportions. We must remind ourselves of proportion. I believe you have learned that one in senior 1, senior 2. When something is, so the assumption we shall take here, we shall take all the components. Take for example, if I want to derive this equation, F is equals to MA. This is the equation we have. If I want to derive this equation, I will assume, I will say, suppose force is directly proportional. Force is directly proportional to mass, product of mass, and acceleration. That's the first assumption I will make. So which means that I will say F is equals to, then I have to remove this proportionality sign with a proportionality constant K. We can introduce a constant K. So now the form will become K M A. Now using dimension, I will first find the value of K. After getting the value of K, then this one will help me. I will find the dimension of each of them, Then after getting dimension of each of them, then I start comparing dimensions. We compare dimensions. We compare dimensions. The dimension, if it's M on the left must be equals to M on the what? On the right. And here we shall look at only the powers. We shall look at their powers. Are you together, members? Are you getting me?
Yes.
Yes. So in deriving equation, we shall look at their powers. Of every quantity. If you are comparing M on the left, you look at the power of M on the right. Then you equate the powers. Equate the powers. After equating the powers, now you use those powers because we shall form equations. We form equations. After forming equation, then we solve the equation. After solving the equation, now we shall get the respective powers. So we shall give powers the names. We can use letters to present those powers. We can use X, Y, then Z. It depends on how you wish. We can use A, B, C to present those powers for each and every quantity. Are you together? Members, are we together?
Yes.
So our interest will be to find the value of X, to find the value of Y, to find the value of Z, or to find the value of A, to find the value of B, or to find the value of C. After getting the powers will help us to determine or to derive that equation. So let's look at the first example there. Let's look at example number one. Example number one. Example number one. Example number one, they're saying here, they will not give us the equation that they have been given because we are the one deriving the equation. So they will just give us the quantities which are considered to be there. That's why they said, assume that the period t depends on the following factors. So periods depends on the following factors. One, we have mass, which is capital M. Then we have length, which is L. Then the third one, we have acceleration. We have acceleration due to gravity. Acceleration due to gravity, which is G. Now they are saying derive the relation between T. They want us to derive the relations, derive the relation between T, M, L, and what? And G. But how are we going to derive that? We are going to use the knowledge of proportion. Because to get this, it must be proportional to the other. It must be either directly proportional or indirectly proportional. But the assumption we shall make here, we shall assume all of them to be directly proportional. Okay? We shall assume all of them are directly proportional. But if it's not directly proportional the way we have assumed, then it will give us a negative power. If it's a negative power, which means it was supposed to be inversely proportional. But if we get a positive power, then it means it is directly proportional to that. But that one we leave it for we shall investigate that. That one will come in the way. But the first assumption we make, all of them, all these three quantities, because they're saying period, so period must depend on mass, length, and acceleration due to gravity of a given string. That one you can also see that. So we shall say, assume T is directly proportional. So we shall have M, I give the power X, L, I give the power Y. It depends on how you wish. Then we go to G, I give the power X. I'm using M, L, then G, because this one are not their dimensions. These are not their dimensions. I'm just putting them as quantities first. Now, after that, we remove this proportionality symbol by introducing a constant. So introduce a constant, introduce a proportionality constant K. We introduce that after making that assumption. So which means our formula now will be T is equals to, I remove that, I become K, okay? M to the power X, L to the power Y, then G to the power Z. This is supposed to be Z to the power Z, okay? I can label this equation as *1. I can label that one as *1. Now, after introducing the constant K, now we go and get the dimension of them. Now we go and get their dimensions. We get the dimension of the period. We get the dimension of K. We get the dimension of M. We get the dimension of L. Then we get the dimension of D. So dimension of T. I said when you're writing dimension, now you introduce a close bracket. So dimension of K for each of them time dimension of M to the power X time dimension of L, to the power Y time dimension of G to the power Z. Dimension of each of them. But remember, K is a constant. And remember, dimension of a constant is, we said dimension of a constant is equals to 1. So even if you are to find out a constant is maybe 100, but its dimension will still be 1. Okay? Are we together, members? Members, are we moving together?
Yes.
Good. So period is time, which means the dimension will still be T. So that one will still be T, capital T, equals to K, which is a constant, its dimension is 1. So that one we leave it out. Then M, which is mass, its dimension is capital M, to the power X, Then length, that is length, so the power is L. Now we use capital L. We use capital L to the power Y, to the power Y. Then we also have acceleration. We have acceleration. If you remember acceleration, we said acceleration is the rate of change of displacement, which is length over time, not so? So
Yes.
acceleration is the rate of change of velocity, sorry. Acceleration is the rate of change of velocity, which will give us L t to the power negative what? 2. Close that, but to the power z, to the power z. Now, if we remember our indices very well, the law of indices, we say when a number is raised to another power, what do we do to the powers? We multiply,
Distribute.
we distribute the powers using what we call the distributive properties. So we use distributive properties. We distribute the power, okay? So which means now we shall have
Yes.
t equals to capital M x L to the power y. Now this one become L to the power what? Z. Then this one become t to the power negative 2 what? 2z. Not so? Members, are we together on that? Now, if you also remember, recall, remember what we are interested here. We are interested in a mass, which is capital M. We are interested in length, which is capital L. We are interested in time, which is capital T. Now, when you look at in the left-hand side, we have only T. What does it mean? So this one is the same as having, it is the same as saying M to the power 0 because still remain 1, okay? Then L to the power 0 because still is 1. Then T to the power what? 1. And this T is the one which we have here. Why am I introducing this? So that we are able to equate the powers. Are you together, members? Because any number raised to power 0 is 1. Any number raised to power 0, so we shall have 1 times t, which still give us back to this. Here we have not changed the meaning. But why am I introducing that? I'm introducing that so that it helps us when we are distributing powers. And when we are distributing powers, we distribute powers per dimensions. M with M, L with L, Y with Y. Are you together, members? Are we together on that? Yes. Equals to.
Yes.
Now, when you look at this one, I have L here, I also have L there. So we can combine this because they have the same base. So we add their powers. So this one will give us M to the power X. Then our L now, L becomes Y. Y plus what? Y plus Z. Then T to the power negative 2Z. Are we together on that?
Yes.
So after writing, question. Yes, please. Yes. Yes.
Teacher, why have you let T to be power 1 and the others are to power 0?
You see, our formula is I sing here, I sing from here. Eh?
Yes.
From here we are still together, right? So what I'm trying to do, because we are looking at the dimensions, which must be of M, length, and then time. So now to make it easier for me to equate, because I'm going to equate what is in the left with what is in the right. So I have to introduce these 3 dimensions. Like now, here we never add time, we never add mass, we never add length. But to make it easier and simple for simplicity, I have to introduce this M and L. So that when I'm equating, I'm able to see it clearly that M is to the power 0, L is also to the power 0. But T will remain this one, which we have here, this T. That's why it's T to the power 1. Okay?
Yes.
Have you got it now?
Yes.
Yes. So I'm only bringing that, but the dimensions still remain this. I'm only bringing this M and L for the purpose of equating them. Okay?
Yes.
So let's start with, we had M to the power 0, L to the power 0, T to the power 1 equals to, what did we have there? It was M to the power X. Then L was what? Y plus Z. Then T we had negative 2Z. Now equating powers. Equating what? Equating powers. So M when you look at m, dimension of m, we look at dimension of m. So m in the left, m is what? M is what? 0, right? M is to the power 0. So that 0 is equals to, what is m to the in the right hand side? Is x.
X.
So which means therefore x is equals to what? X is equals to?
X equals to 0.
X is equals to 0. So that's now because we are looking for x and y, z. Okay? So which means x is already 0. Then we come to dimension of L. So when you look at dimension of L in the left we have 0, so we shall have 0 equals to, in the left hand side, what do we, in the right hand side we have y plus z, not so? So it implies that our equation, which is y plus z, is equals to 0. We can label that one. We can label this one as equation number 1 because we don't know y and z yet. Okay? So we also go ahead and look at dimension of dimension of t. So when you look at t, in the left hand side we have t is to the power 1. T is to the power 1, which means the power is 1 there, equals to. In the right hand side, what do we have? We have negative 2. Negative 2z. So it implies that negative 2z is equals to 1. So we divide also by negative 2. Divide also by negative 2. I think that. So which means z is equals to negative. Z is negative what? Negative a half. Negative a half. Now what is missing? We know the value of x. We know the value of z. So what is missing is what? Y, right? So we come and say from which equation is that? Which equation? Equation 1. From equation 1, which is it? Y plus z equals to 0. So which means if you make y the subject, we shall have y is equals to 0 minus z, which means y is equals to negative what? Y is equals to negative z. So y will be equals to negative into, what is the value of z? Z we got negative a half. So you find that negative times negative must give us a positive. So our y is positive what? Is positive a half. But now, when you remember from our indices, so let's look here. We have got, therefore, x is equals to 0, y is equals to a half, and z is equals to negative what? Negative a half. Now, when we recall from our indices, I said any number to the power half. If I have a to the power half, that one we write it as square root of what? Of a. If I have any number raised to the power a third is equals to the cube root of what? Cube root of a. Do you remember that concept in mathematics? Do you remember that?
Yes.
So if that one is true, now we come back here, we come back to our equation. Remember, we are deriving equations. So we said since t was equals to k, okay? Now here you go back to the formula here. You come back here. I think where the cursor is, here, okay? You come back there because now we were looking for the power of m, but for us to help us to get the powers, we have to get the dimensions. So now we have got the powers, which is x, y, and z. Now we come back to the original equation. So k, which is equals to m to the power x, l to the power y, then g to the power z, So it implies now our t, we shall have k, m, x we go to the power 0, l we go to the power half, g, z we go to the power negative a half. Now also, if you remember, if I want to remove this negative, it's like if I have 1 out of a, we said it's the same as 1 out of negative 1. Not so. So which means I have to get the reciprocal of this. When I get the reciprocal of this, the power will become positive. Which means I'll have t is equals to k m naught l to the power half So I get the reciprocal of this, which will become, this one become d to the power positive I have now. Okay? Are you together? Members, are you together? So we shall have t equals to, so we shall have k. Now any number raised to power 0 is 1. So this one will vanish. Then we remain with L out of D, but all of them, because they are raised to the same power, which means I can distribute the powers. When you recall from this, indices is very important. I said if I have A over B to the power n, we can say it's A to the power n, B to the power n. Okay? So here we distribute, because they are under the same power, which means I can write it like this. So this is what I've done here. But we know that square root, I have, is the same as a square root, like we have seen there. Like we have seen here. Any number raised to power half is a square root of that. So this means therefore our t will be equals to k. Now instead of writing a half, I will just write the square root of L over D. That's the equation we have derived. As simple as that. So this is what we are deriving. So don't you think it's true? When you are getting a period of any, maybe you are getting, you are determining acceleration due to gravity, you are determining period of a given oscillation. It depends on the length and acceleration due to gravity, but is inversely proportional to acceleration due to gravity, because remember the oscillation is against gravity, if you remember that principle very well. Okay, are we together, members?
Yes.
So what is important here is the law of indices. You first assume, because now even when you look at in our formula, we didn't assume that this was going to be L over G. But because of the process of indices, we discovered that this formula was supposed to be the square root of L over G. Why the square root? Because it's to the power a half. And we know that any number raised to the power half, a square root means a number is raised to the power half. Cube root means a number is raised to the power a third. Fourth root means the number has been raised to the power a quarter. Fifth root means the number has been raised to 1/5. Just like that, just like that. So you have to take note of that. So that's how we derive equations. That's how we derive equation. We said dimensional analysis does not give the value of a constant, K. It can only be determined using mathematical analysis. So when we talk of dimensions, dimension will not help us to find this. Okay, we just leave it as a constant, K. Okay, don't bother yourself because of dimension when getting this constant. But when we go to the formula that we have been using, we find that here is supposed to be 2 pi. But that one is not what we are looking at now. That one we shall look at it when we move to the second part, which is motion. We shall understand that one when we come to motion. Okay? Are you together, members? Members, are we together? Sandra, are we together?
Yes, teacher.
Okay. Now let's move to number 2. Example number 2. Example number 2. Number 2 is there. Question number 2. That's saying use dimensional analysis. Use dimensional analysis to show how the velocity of a transverse vibration of a string, of a stress string, depends on it. So which means we want to, what we have, one of the quantity that we have is velocity. We have velocity there, V, okay? Now this velocity is depending on the following factors. Depends on one, we have, they have given us length, L. They have also given us mass, M. They have also given us tension. We know that tension is the same as force. Take note of that. Tension is the same as force. And I've used capital letter F. In the string. So like I've said, we first assume that the velocity V is directly proportional. It's directly proportional to, now we give powers to each of them. We give power to each of them. It depends on L, which we shall give it to the power X. Or I can use A. Let's use A to the power A. Then M to the power B. Then F to the power C. F to the power C. Okay? Then what we do, we remove the proportionality sign. So it becomes now V is equals to K. Okay? K, L to the power A, M to the power B, then F to the power C. After writing now the formula here, this one we put it as star. This is the equation we have. But now the only thing missing in this equation, the powers of A, the powers of B, and the powers of C. So, but to help us find the powers A, B, and C, we have to use dimension. Now we get dimension of each of these quantities. We get dimension of each quantities. We get dimension of each of them. So we get dimension of V equals to dimension of K equals to times dimension of L, but it's to the power A, times the dimension of M, which is mass, but it's to the power B, then times dimension of force to the power C, like that. So what is the dimension of velocity? We said velocity is the rate of change of displacement. So it becomes L to the power -1, right? Not some members. Let's contribute, please. Let's contribute. Equals to, what's the dimension of a constant? Dimension of a constant is it?
Is 1.
Is 1. Now this is length. What is the dimension of length? Is what? Capital letter what?
L.
Capital letter L to the power A. What's the dimension of mass? Is what? Capital letter M. B. What about force? Who can give us dimension of the force? Dimension of force? For the instance of time, let's just check from here. Force, are you seeing it here? Force is M. L to the power negative what? -2. But it's to the power what? To the power C. So we shall have L T power -1 equals to, this one will not change anything. So we shall have L to the power A, M to the power B. Now when we distribute this power, we shall have M to the power C, L to the power C, then T -2 what? -2C. Right together, members?
Yes.
So we shall have L power -1 equals to, now here we simplify them. We bring L together. I have L here, I have L there. So this one will give us L, A plus what? A plus C, because
C.
here is A, there is C, right?
Yes.
Then we go to M. M here I have B, then what? C. So it becomes B plus C, right? Then T is standing alone, which is 2 to the power -2C. So when you look in the left, what is missing in the left? M is only M which is missing, right?
Yes.
So that one is the same as having M to the power
0.
M to the power 0, L, then T to the power -1, okay? Equals to L, A plus C, M, B plus C, then T to the power -2C. Now we start equating powers, We equate powers dimension by dimension. So dimension of M. So let's start by dimension of M. M in the left, M is what? 0. Equals to, what do we have in the right? In the right, we have B plus C. So which means I'll have B plus C equals to 0. That one is our equation number 1. As we call that one equation 1. Then we go to dimension of L. Dimension of L. In dimension of L, what shall we have? We shall have
-1.
1, not so, because here is to the power 1. I think this one, okay, is to the power 1 equals to, which is 1 a plus c, okay? So it implies that a plus c is equals to 1. So this one become our equation number.
Excuse me.
Yes?
Then the L negative 1.
Yes?
Then the L
L is not negative. L is not negative, please. I sing here. I sing from here.
is negative 1.
Is t, which is negative 1, is t, not L. This is the same as to the power 1. Okay? Have you seen that?
Yes.
Have you seen? All right. Now let's look at dimension of t. Dimension of t. So when you look at dimension of t, in the left we have negative 1. The power is negative 1. Then in the right we have negative 2c. We have negative 2c. So you see that for this one we have only one unknown. So which means it implies that negative 2c, which is equal to negative 1, when you divide also by negative 2, you find this and this will disappear. So which means c is equal to negative and negative will disappear. So we shall have a half. So c is a half. Now, which equation should we use? We can use equation 2 to get the value of a. So from equation 2, which is a plus c equals to 1, which means a is equals to 1 minus c. So it implies that our a will be equals to 1 minus a half. 1 minus a half. What is 1 minus a half? Members, what is 1 minus a half?
A half.
Is a half. So which means a is a half. A is a half. We are left with it. We know the value of c. We know the value of a. We are left with it, the value of b. But how do we get b? We come here. Okay, we come back to this equation 1, which is b plus c equals to 0. So from equation 1, which is b plus c equals to 0. So which means b is equals to 0 minus c. So b is equals to negative c. Okay? So it implies that b is equals to negative into our c, which we got a half. C is positive a half. So therefore, b is equals to negative what? B is negative what? B is negative. B is negative a half. So we have got A. We have got A, we have got B, and we have got C. Now we come back to our equation. We come back to our equation here. Where is number 2? We come back to our equation here, where we said from star, it was in star, from star, where we said V is equals to K L to the power X, to the power A, M to the power B, then F to the power C. Do you remember that? Members, do you remember that? So now we substitute the powers back. We shall have V equals to K, V equals to K, L. What is the value of A? A, we got what? We got a half, right? M, what about B? What did we get B? What was the power of B?
Negative a half.
Negative a half. Then F, what was the power for C?
A half.
It was positive a half. Now you see this one is a negative, but I want to remove this negative. I want to remove this negative so that I can write a correct formula. So that I can write a correct formula and equation. So we get the reciprocal of M. Okay? We get the reciprocal of what? M. So when we get the reciprocal of M, we shall have V equals to K L to the power a half, then F to the power a half over M to the power a half. Now you can see all the powers that are the same. You have a half, a half, a half. But this one is now positive. But here from here was negative. But by getting the reciprocal, it became a positive. So we shall have V equals to K into, now we'll put them under one bracket, L M over F, but to the power, LF over M, but to the power a half. Okay? So, but we know that a half, any number raised to power half, that is a square root. That's a square root. So therefore, V will be equals to K square root of L F over M. So that will be our formula. Have you seen that? Members, have you seen that?
Yes, teacher.
Sandra, Narubek, have you seen that?
Yes, teacher.
Okay. So we shall go for a break. We shall go for a break.